Hello everyone, my name is Brant Kudrowski, and this organic chemistry lab video covers an organic spectra interpretation experiment. This is part 2, solving an example unknown. In the previous video, we introduced this experiment and also went through a number of different tables of spectra data that you can use to interpret unknown spectra. We'll be using that information in this section to solve an unknown. What I'm going to show you here is a strategy for solving unknowns with multiple spectra. It's not the only way to approach these problems, but it's a strategy you can use, and if you develop your own techniques, that's great. I'm going to start with the mass spectrum and just try to get as much information out of it as quickly as I possibly can. Start by identifying the molecular ion region, which is the area with the heaviest substantial peaks. This region around 72 is the molecular ion region. Label the molecular ion, that's the M+ peak. That's the entire molecule that's just lost an electron, and determine whether it's even or odd. So here we have a 72 peak, that's even. By the nitrogen rule, we can say that this molecule contains an even number of nitrogens, either 0, 2, 4, etc. The next thing to do is to look for isotopic peaks that you can find associated with this molecular ion. For example, an M+1 peak would be due to carbon-13 incorporation, and we can see a little M+1 peak here at 73. You also should look for an M+2 peak to see if there's any substantial peak 2 mass units heavier, at 74 for example. Since we don't see a significant M+2 peak in this spectrum, we can say that there isn't chlorine or bromine present. The next thing to do is to label the base peak and think of possible structures for it. The base peak is the strongest peak in the spectrum, and it's set to 100% intensity. This is a significant peak to try to understand because it's the most abundant cation in the mass spectrum. It's probably the most stable cation that can form from the structure. In this spectrum, the base peak is at 43. These are some possible structures of cations that weigh 43 from the table I provided in the previous video. At this point, we don't know which one is more correct. We're going to have to come back to this ion later on to assign it definitively. It's just good to know that these are some possibilities for what it could be. You might also get some information out of the peaks at 29 and 57. These can be helpful, but don't get bogged down trying to figure them out. The peak at 29 could be an ethyl group, for example. The peak at 57 could be a butyl group, but don't try to figure out every peak in the mass spectrum. You'll be frustrated. Try to quickly size up the molecule from the mass spectrum and then move on to your other spectra. You can always come back to the mass spectrum later. Next, we'll go on and take a look at the IR spectrum and try to learn what kinds of functional groups are present in this molecule. Focus your attention on the functional group region of the spectrum, which runs from 4,000 wave numbers down to 1,500 wave numbers. The fingerprint region is below that, and usually the peaks in the fingerprint region are too difficult to interpret. The one exception is if you find a very strong peak in the fingerprint region between 1,200 and 1,050, that could be a CO peak. That might be useful. But for the most part, you want to just ignore the fingerprint region. Then try to identify all the major peaks in the functional group region. What I suggest doing is writing an imaginary line up from 3000 and taking a look at what kinds of peaks you have on either side of it. Alkyl groups have sp3 hybridized carbons that have CH bonds that show up just a little below 3000. We do have peaks in this region, which means the molecule likely contains an alkyl group and has sp3 hybridized carbon H bonds. Now, most molecules actually have alkyl groups, so this isn't too illuminating, but it is something that's good to keep track of and know. sp2 hybridized carbon H bonds show up on the other side of that red line, slightly higher than 3000. You can see here we don't have any of those. That suggests that we might not have a double bond like an alkene or an aromatic ring. However, the absence of a peak doesn't tell you that the functional group isn't there. If a vibration doesn't give a significant dipole change in the molecule, it won't show up as a peak. So it's possible to have a particular functional group in a molecule but not see a peak for it. The bottom line is you have to be a bit careful about interpreting negative evidence in IR. There's one really large peak in the functional group region of this spectrum, and that sits around 1710 or so. If you take a look at the table of IR peak frequencies that I provided in a previous video, this could be 3 different carbonyl groups: aldehyde, ketone, and carboxylic acid. It's a little too low for an ester carbonyl. Aldehydes, ketones, and carboxylic acid functional groups can be distinguished in IR by looking at the peaks that would go along with the C double bond O. An aldehyde would have a pair of peaks at about 2720 and 2820, and we don't see those here, so this would not be an aldehyde. For carboxylic acids, there would be a really big peak centered at about 3000 that would be extremely broad and jagged. We don't see that either, so this can't be a carboxylic acid. Therefore, we're left with ketone as the most likely possibility. Finally, since we have a ketone, you should be on the lookout for an overtone peak. That's what I'm pointing to right here with the blue arrow. The overtone peak shows up with carbonyls frequently, and it's twice the fundamental frequency. So if we have a 1710 peak, this comes at about 3420 or so wave numbers. It's important to be aware of that peak and not confuse it with a CH or OH or other kind of functional group. So after looking at the IR spectrum, we have a sense that this is a molecule that contains a ketone and alkyl groups. At this point then, we've learned as much as we can from the IR spectrum, and we should move on to the NMR spectra. This is the Proton NMR spectrum of unknown A. NMR is a powerful technique for determining molecular structure. It provides detailed information that can be used to establish the connectivity of the molecule. Usually the Proton NMR spectrum is the most powerful piece of information that you have, and sometimes you can solve the structure from the Proton NMR spectrum alone. Proton NMR spectra contain 4 kinds of information. First, there's the number of signals that you see. That gives you the number of unique types of protons. Protons in different chemical environments give different signals, whereas protons in the same chemical environment give you the same signal. So the number of signals tells you how many unique types of protons you have. The second type of information that you get is integration information. That's the area under the peaks. The area of each signal will give you the relative ratio of the number of protons represented by those signals. Then there's chemical shift information. These are the values on the x-axis, and it's in parts per million. The chemical shift value of a signal tells you the type of chemical environment that the protons are in. For example, are they in an electron-rich environment or electron-poor? Are they near an electronegative element or not? Are they near a double bond or not? That's the kind of information chemical shift provides. The final type of information that you get out of Proton NMR is splitting information. Some of these signals are single peaks, and some of these signals have been split into multiple peaks. The splitting tells you about the neighboring protons. There's something called the n+1 rule that states that protons that have n neighbors, where n is some integer number, are split into n+1 peaks. For example, if you're a proton and you have one neighbor, you're split into 1 + 1 or 2 peaks, so your signal would be split into a doublet. Every peak in a Proton NMR spectrum means something, and you should try to get as much information out of each as possible. Think about these 4 different types of information as you're going through and looking at the signals. When you approach an NMR spectrum like this, I suggest the first thing you do is label the signals. Label each signal in the spectrum with a lowercase letter starting from left and moving right, A, B, C, D, and so on. This spectrum has 3 signals, which means there are 3 different types of protons. There are protons in 3 unique chemical environments that we'll be looking for. The next thing I suggest we do with this NMR spectrum is to determine the integration values. Integration information comes at you a couple of different ways in NMR spectra. Sometimes it's listed as a number that sits above the peak or below the peak. In some cases, it's described in integration traces that run above the peaks, and that's the case in this spectrum. These squiggles that are appearing above each one of the signals is an integral trace, and the height of that trace gives you the relative ratio of the protons represented by that signal. We'll need to get out a ruler and measure the heights of these traces. I'll start with the signal A. The distance from the bottom of the integral trace to the top of the integral trace is represented by this blue arrow. If we put a ruler on that, we can see that that distance is 4.9 centimeters. I'll draw that above the integral trace. If we do the same thing with the other signals, signals B and C, we get 7.3 centimeters for signal B and 7.3 centimeters for signal C. These numbers represent the ratios of the areas of the peaks. A to B to C is equal to 4.9 to 7.3 to 7.3. This is an accurate ratio, but it's not a whole number ratio. Molecules don't have fractional protons, they have whole number ratios of protons, so we need to convert this ratio into a whole number ratio. The easiest way to do that is to first divide each value by the smallest value. So in this ratio, we'll divide everything by 4.9. That'll give us values of 1 to 1.49 to 1.49. Now this is still not a whole number ratio, but it's closer. If we were to multiply each one of these values by 2, we would get something that's very close to a whole number ratio. It's 2 to 2.98 to 2.98. That's essentially 2 to 3 to 3. This is the whole number ratio of the protons that are represented by signals A, B, and C. They're present in a 2 to 3 to 3 ratio. I'm going to write these numbers above each one of the signals in red, 2H, 3H, and 3H. It's important to note that this is the simplest whole number ratio of the protons represented by the signals. The actual number of protons might be different. It might be some larger multiple of this. For example, you could have 2 to 3 to 3 actual protons, or you might have 4 to 6 to 6 actual protons. It depends on the molecular formula of the molecule, and we don't know that yet. When we go through and try to figure out what protons these signals represent, we're going to be looking for 3 of the type C, 3 of the type B, and 2 of the type A. The signals that represent 3 protons are very likely from methyl groups, CH3 groups. The signals that are 2 protons in intensity could very well come from a CH2 group. This is helpful information to know, and it's really pretty easy to get. Next, we're going to look at the chemical shift values of the signals to try to get an idea about their chemical environment. The table that I provided in a previous video can help, but it isn't definitive, and you have to be careful how you interpret it. For example, there are many proton signals that show up near 2.5, which is about where our signal A appears. Here's a portion of the table that I provided to show you what I'm talking about. There are a number of different proton types that appear near 2.5 parts per million. And if the Proton NMR were the only thing we had, you wouldn't really know which one it might be. However, if you remember back to the IR spectrum, we found a carbonyl in this molecule. We're pretty sure it has a ketone in it, and so that makes this particular entry especially likely. One of the skills in multispectral interpretation is taking what you learned in one spectrum and applying it to another spectrum and looking back and forth and trying to find consistencies, information that's coming at you a bunch of different ways. Signal A very well could be protons that are on a carbon next to a C double bond O. Signal B is in that same region, protons that are on a carbon that are next to a C double bond O, and that would be consistent for a ketone. Signal C is probably due to protons that are further away from a deshielding group. They're not next to a double bond, for example. Next, we'll use the splitting information in this spectrum to help us determine how the atoms are connected. We'll use the n+1 rule to determine the number of neighbor protons for each signal. To count as a neighbor proton and to cause splitting, protons usually have to be within 3 bonds of each other. There are exceptions. There are some instances of splitting that occurs over 4 or more bonds, but it's less common. Look for protons that are 3 bonds away to serve as neighbors. We'll start with signal A. Signal A is split into 4 peaks. That's called a quartet. That means that there must be 3 neighbor protons next to the protons that are signal A, because 3 plus 1 equals 4. This quartet is telling us that there are 3 neighbor protons. These 2 H's, they have 3 neighbors. Signal B is a singlet. That means it has no neighbors. 0 plus 1 is 1. These are isolated protons. This is probably a CH3 group that is not near any other protons. And finally, we have signal C. That's a triplet. That means that this signal has 2 neighbors. From the integration, we know that this is 3 protons, and from the splitting, we know that these 3 protons have 2 neighbors. It's a CH3 next to a CH2. Now we need to use this information to determine fragments and then put them together to form a molecule. Let's start with the signal B because that one's simple. We determine this is a CH3 group that's isolated and doesn't have any neighbor protons nearby. Signals A and C are coupled to each other. They're splitting each other. Signal A is from 2 protons that have 3 neighbors, and signal C is 3 protons that have 2 neighbors. This must be a CH2 group that's next to a CH3 group. This is what you get for an ethyl group. As you go through and solve structures, you're going to learn to recognize certain patterns, and the ethyl pattern is one that's going to be very useful. A quartet that has relative area 2 and a triplet that has relative area 3. These 2 fragments have to be connected in some way, and we know from the IR spectrum that we have a ketone, so in the middle sits a carbonyl. Having the 2 fragments bound to a carbonyl also is consistent with the chemical shift values. Signals A and B are in a region of the spectrum where they're deshielded by the presence of a double bond. Having the carbonyl group where it is makes sense from a chemical shift perspective. I'd like you to assign your proton values as I've done in this example, where each signal has a letter label A, B, C, D, etc., and your structure shows all the protons drawn in with corresponding letter labels next to them, with an A by the protons in the structure that give rise to that signal, a B next to the protons in the molecule that gives signal B, and so on. Now we're going to look at the C13 NMR spectrum of unknown A. C13 NMR is analogous to Proton NMR, but instead of looking at proton nuclei, it looks at carbon-13 nuclei. There's only 2 types of information in a typical carbon-13 NMR spectrum: the number of signals, which gives the number of unique types of carbon, and the chemical shift values of those signals. Peaks in carbon-13 NMR are typically not integrated, and there's typically no splitting observed in a C13 NMR spectrum. The reasons for that are beyond the scope of this class, but it means that carbon-13 NMR spectra are a lot simpler to interpret. Here we have 4 peaks for unknown A. The first thing I would suggest doing is labeling these signals, but use capital letters A, B, C, D, etc. So I'm going to label those signals from left to right with A, B, C, and D. There's typically no integration or splitting info contained in a C13 NMR spectrum. You should look at the chemical shifts of the signals to get ideas about what kind of chemical environment these carbons might be in. The tables of chemical shift values that I provided in a previous video can help, but it often isn't definitive because sometimes a signal could be from multiple different types of carbons. We look here for some of the possible chemical shifts. Signal A really stands out as being unique. It's way out at about 215 parts per million. That's consistent with an aldehyde or ketone carbonyl carbon. We know from the IR spectrum that we have a ketone, and we discovered that in the Proton NMR spectrum that there were protons that were deshielded based on being next to a ketone. And if you think back to the mass spectrum, we even had a fragment at 43 that was from a ketone fragment, the acylium ion. So we're getting a lot of the same kind of information here from multiple different sources. The peaks B, C, and D are from carbons that are in more shielded type environments. These are from sp3 hybridized carbons. In carbon NMR, it isn't always possible to assign all of the signals definitively. It's probably true that B and C are the two carbons that are close to the carbonyl, and D is the carbon that's furthest away. It's also probable that signal B is from the CH2 carbon, and signal C is from the CH3 carbon that's next to the carbonyl group. To assign the carbon 13 NMR spectrum then, I'll put a capital letter A next to the carbonyl carbon, I'll put a capital letter C next to the methyl group that's closest to the carbonyl, a B next to the CH2 that's closest to the carbonyl, and a D on the carbon that's furthest away that's in the most shielded environment. Now we can return to the mass spectrum and address what is that base peak that we were looking for. We said that there were three possibilities for this peak, three different kinds of fragments that could weigh 43. There's a normal propyl group, an isopropyl group, and this acylium ion. The acylium ion is a really good choice because this acylium ion that weighs 43 comes from a methyl ketone. So now we can assign the base peak structure definitively. One last piece of advice is when you have a structure that you think is right, make sure you go back and double check and make sure that it's consistent with all your spectra data. Sometimes you can get something that's a pretty good fit but doesn't quite work. In those cases, you should revise your structure and find something that fits with everything. The next video in the series is going to contain unknowns B through H, and I will give you those spectra and I will give you little hints on how to solve those spectra, but ultimately you'll be solving those structures on your own. If you found this video useful, check out the next one in the series or watch the prior video, and consider subscribing to my YouTube channel. My name is Brant Kudrowski. Thanks for watching.